Are you managing? Are you being able to be organized? Maria, don't you feel better than last week? Yes, Kausar, what's your question? Would you want to unmute yourself, Kausar, to speak? One second, my laptop was on mute. Probably you were talking. Okay. Can you please repeat?
Yes, last time I read on the group that you said that the exam is on 27.
Okay.
خلاص, is it on 27 or 20? Just to know, يعني.
Yes, so definitely, since we have a meeting now, the things I need to talk about are the following. One, the midterm and everything related to the midterm. Two, we need to discuss if you have any questions about Lab 5. Three, we need to look at our schedule and see how things are. And four, we're gonna start a new lab. So definitely, let's start. I'm sorry for the students who spoke to me a few minutes ago before Kausar. My laptop was on mute. I had no idea you guys were talking. And I was asking how good you are, and nope, everybody was silent. I was worried. Okay, so the midterm. Let me explain. I wanted to push for it to happen on the 20, and I know 20 probably is the best time and date for you, but we cannot do that for many reasons related to how close March 20 is and how not appropriate it is for the other sections. So I know for a fact that 20 is not possible anymore, and I'm sorry for this. I know you wanted 20. Now they wanted to push for the 27, which is another Saturday, and I had a lot of complaints about it, not from you directly because I just met you, from other students, the other sections. That's why I didn't even ask you about the 27, because I understood it was really bad, and they asked me to push for the 29, which is a Monday. I know 29 is not the best date, but it's definitely better than 27. And the midterm, yes, is going to happen on Monday, the 29 at 7 p.m. And I was waiting to see you to explain what we went through all this week to finally decide on a date and time. And again, I know it's not good for a lot of students, but I also know it's not good for us not to have an actual date, because not having a date will make you not being able to focus and organize yourself. For the students who are not so little, like you are many, I know, for the students who have an exam the next day on Tuesday, I know it's going to be tough on you, but now that you know what you have in 2 weeks, probably you can organize yourself. Now, how can I help you organize yourself? You need to understand, if you're doing those lab reports alone, you don't really need to study for a midterm in the physics lab. I need to remind you, we have lab 1, 2, 3, and 5, so only 4 labs. Most probably it's going to be multiple choice, around 20 questions. Um, a lot of it will be conceptual, like what happens if you vary this, how does it affect whatever, or probably how do you believe the sketch of this versus this would be, and I will give you the options and you pick from these, you know. A lot of questions will be conceptual, and a lot of questions will be data analysis, like I give you values, you need to know the average, the RMS. Okay, so if you know how to do the data analysis well, that's 90% of the exam. You're ready for 90% of the exam. You just need to go over the chapters quickly, like what about chapter 1, the projectile motion, the important concept, incline, motion on an incline, important concept, and so on. So I don't, and probably what I can do, and that was something suggested by the Monday section, I can send you like a checklist or like a feedback about those experiments, the common mistakes, what you need to know for you to be able to study in a shorter time. And I'm gonna do this anyway. Now concerning Excel, yes, I've been talking to the admin, to the other instructors for the whole week, and this is what we got. We have to use responders. There's no way out of it. No, we cannot use Excel anymore. There's no way out of this one. Now, what you need Excel for? One, you need to find the slope, and this can be done on the calculator. Even if you don't know how to do it, you can learn in a short time. Probably it will take you less time to do it on a calculator. I'm talking about the slope only. The RMS, you need to do it on the calculator anyway, and probably it's faster if you do the RMS directly on the calculator anyway, you have no other choice. Sources, propagation of error, you have to do the calculations anyway. Plot, most probably you will not be asked to do any plot, it's multiple choice again. So the only remaining thing is the error on the slope. The error on the slope can be either done by using the equation or an Excel spreadsheet, or the linest function that I believe is very fast and awesome. And I know for a fact that 20% of you don't know how to use it yet. Or simply I can skip the error on the slope in this midterm. And I'm not upset because of that, because I know you are being trained to use Excel not for the midterm eventually because you need it, and because the midterm is, I mean, the lab reports is like 90% of your semester work. And the midterm is not our only purpose and our only objective, if you know what I mean. So yes, I want you to be very well trained for the on Excel for anything you need it later on for any other science lab you will take in the future. And it's okay if we're not going to use it for the midterm, it's not going to be a big deal. How about we avoid error on the slope in the midterm, for instance. Now, if you want to know more about the midterm, how many questions, the style of the questions, what to cover, and so on, let's talk about this next Tuesday, because by then I would know a lot more about the midterm. Okay? So I was I was hoping for the ideal date and ideal time. And trust me, it's a bad timing and date, but trust me, this is better than some other date the other sections were pushing for. Okay? Yes. Why not 27? Because a lot of students have a lot of exams on the 27th, that is a Saturday. Okay? And we were fighting on the timing as well. Yes, I wanted 27 to be honest, Carl. But 29 is not ideal for me. It was better for the majority, not for everybody. Okay? Yes. Any questions concerning the midterm I can answer now or next Tuesday? All right. The second item on our agenda is to discuss any why not next week. Okay. You need to know that some sections are a bit behind, and you are one of those sections. But many other sections as well. And you need to know that some sections do not know how to use their calculators, and they requested one extra week to train. But I believe that's simply an excuse. It's simply that we need more time, that's all. You have the first 4 experiments, and many of you are still submitting the 5th experiment, you know? So you need feedback for it. And if 20 is the exam, which is Saturday, it's like in few days, it's too early. Okay? We wanted to do it early for you to have an idea about the midterm grade and so on, but pushing the thing early was not convenient for many sections. We are too many sections, and this is really difficult to handle. It's not the same for other courses. Of course, I can help you, Rita. Can you please, after class, send me a picture of your calculator, and I can send you any YouTube video to watch, or I can do it myself on a very small video. Otherwise, we can meet after class to discuss your calculator. And trust me, it's gonna be really, really quick. Okay, and you can write the steps on a paper for you not to forget them. But Rita, don't forget to send me a picture of your calculator via email or WhatsApp or any other platform. Yes. So we're still talking about the midterm. Any questions or comment or concern concerning the midterm? And we can meet anytime you want. Concerning the lab reports, I'm finishing correcting lab 2. Actually, I'm done. I still have 3 students only. Hopefully you're not one of those 3 students. Otherwise, I'm going to continue after class. I want everybody to be done with lab 2 so I can start with lab 3 as well. All right. Shall we discuss lab 5? Let me open the manual a bit. Manual is here. It was open. I'm sorry, I closed it. the last two questions in lab 5. By the way, Marilyn, I still have to answer your linist question. By the way, you see it, it's open here. I did not forget, I simply did not have the time to look into it yet. Okay, so I'm opening lab 5 for you, simple harmonic motion, right? You want me to explain the last two questions. Okay, last two questions. All right, in question number 3, they want you to discuss how 10 oscillations, 20 oscillations, and 40 oscillations will eventually affect your amplitude and the damping on the period, like amplitude and period. You know, after 20 or 40 oscillations, damping is gonna be really visible. Like friction is gonna affect a lot your motion. The question is, how does it affect amplitude, friction, and how does it affect the period? As friction is getting more and more and more into your system and affecting your system more and more through 40 oscillations, probably after 40 oscillations it's gonna stop. How do you believe the amplitude is gonna change and the period is gonna change? Does it make sense for question number 3, Marilyn? And for question number 4, they want you to sketch, and by sketch, they want you to show the behavior in general. So please don't feel bad of using a pencil to do so. So sketch the general behavior of the displacement versus time, which is a sinusoidal function that you can start from anywhere. You can start from 0. So I don't care about the initial conditions. Draw it with damping and without damping, which means with friction and without friction. Damping means friction, right? So it's like a continuation of question number 3. You know, friction may affect amplitude or not. It may affect period or not, okay? Do some reading about that. This is mainly covered in high school, grade 12, for instance, probably in grade 10 a bit, I don't know. But yeah, it's a general conceptual question that could be included in a midterm, but definitely with A, B, C, D to pick from, okay? All right. So now Kausar is asking about question 1, propagation of error of the formula. I love this question. My favorite. Question 1, I suppose you're talking about the pendulum, right? Yes. T theoretical.
Yes.
All right. So let me write it down. I know
I did it. I don't know if it's correct. I tried to Google it, but I don't know if it's still correct or
I
not.
don't know if you can find the propagation of error on Google.
No, I did the derivative of مثلا radical of x over constant and then
yes.
over x. Yes.
That's the right track. I'm gonna separate radical L and radical G to probably make it easier. Okay, and let's create some space. It's stupid to write on word on the, yes, and I'm gonna move this up. All right, so I suppose your problem is with the derivative. So I'm gonna start constant times radical x. What's the derivative? Okay. All right, so let me see. I'm sorry if my pen is slow. It's due to the recording. Usually I have the greatest pen on earth. All right, so how do I do the derivative? K is gonna stay. The power is half, so I have half. And then I will have x to the power of half and minus 1, then it's gonna be minus half, right?
So it's take 1 over radical of x.
Yes, so it's gonna be k divided by 2 radical x. Okay, that's if the x is in the numerator. Now, if the x is in the denominator, I'm gonna do the same thing, but I will consider that x is to the power of negative half and do the exact same thing. So it's gonna be k is gonna stay, and then I'm gonna have negative half, and the power of x, it's gonna be the power of x to the negative 3 over 2. So if you want, I will put it here, which will be x radical x. Or how about you write it simply x to the power of negative 3 over 2 and keep it. You have a calculator. Let the calculator do the work. Why do it yourself? Honey, you can keep it x to the power negative half. Put it in parentheses for the calculator to take it well. Okay? And the minus is not going to affect your work because it's going to be squared eventually. Yes. Yeah, try it. It will work. It's big, I know. Take your precautions, use a lot of parentheses. I know math instructors would roll their eyes on me, but use them. They're for free. Use them a lot just to be on the safe side, okay? Because calculators are not very flexible, I know. Like
Doctor, is it normal? I know the error on the T theoretical, to be by decimals I'm speaking, different than the experimental one. Yes. And for example, let's say it's 0.01 for T theoretical, and for T experimental, let's say it's 0.0002, for example.
All right. I need to explain something very important. Thank you for this very smart question. The error on T theoretical is related to the error on L and the error on G. Yes. All right. So the bigger the error on L and G, the more error you have on T theoretical. However, if you look at T average, it's related to the fluctuation you have here, the scattering. If the values you get here, here, and here are far away from each other, expect an RMS error to be a bit bigger than expected. So the error here and the error here, they have nothing to do with each other, because this is a simple repetition with different M's, right? But the T should be the same. So it's basically like repeating the experiment, not the exact same experiment, but it's the procedure is different. Here you only have one measurement of L, one measurement of G, and you're calculating T. So ما خصهم ببعض, they have nothing to do with each other. Okay? So it's random. This could be bigger than this, or this could be bigger than this. Maria's asking, do we have to find the uncertainty of T in the table? For each and every, no, because they don't ask me about it. Also, because I don't see how it's going to affect my final answer. It's not going to affect my final answer. And this is why they did not ask you to find the uncertainty for each. Okay, Hala, if you would like to do it to understand what you're doing, remember this lab report is a template and this is the minimum required. You can do much more if you have a need. Some of the students would say, I need to find the uncertainty to be able to round or to be able to analyze my values. So this is the minimum required. You want to do more, you can. You want to do the minimum, you also can. It's up to your needs. Yes, propagation of error. So basically, Carl, we did not do the propagation of error. I simply showed Kausar how to do the derivatives. Now, Kausar should do the extra mile and do the error on T is derivative of T with respect to L times alpha L, all of it squared, then derivative of T with respect to G, and times alpha G, all of it squared, and then add them together and do the radical. To do the derivative of T, so this is similar to derivative of T with respect to L. Okay, right? And this is the derivative of T with respect to G. Okay, so you can simply replace K by the constant. In this case, the constant is 2 pi divided by radical G. You replace X by the variable that is L in this case. And K for the next one is, if G is the variable, everything else is the constant. Okay, now, Carl, I know probably I did not answer your question fully. What I advise you to do it on Scratch, send it to me, I correct it for you, I give you hints. This is what I usually do with other students. Okay, so I give you a hint. All right, it worked, really? Can you tell me, Marilyn, what was your mistake? You simply repeat it again and it worked? I didn't even look at it. It's here, I didn't look at it. All right, so it's part of selection. Other than something you selected, because usually students would, for you to be able to find the Linus, you have to click Command Shift something, and it's different on different iOS. So I thought probably that was your mistake, and I wanted to try, but I couldn't. I did not have the time for it. Anyway, I'm glad it worked. I wanted you to share. Yes, on Mac, it's Control Shift Enter. Yeah, I don't remember Marilyn was using Windows, I suppose. All right. Anyway, if you know how to do it on your computer, yeah, so Marilyn was selecting something else. Anyway, I advise everybody to learn how to use it. It's fast. You have 10 lab reports, 2 exams. You're doing it for the 10 lab reports, not for the exams, okay? All right, for the students who did not try the Linus function, please do so in the near future. It gives you a lot of extra time. It's great for lab reports, okay? Otherwise, use the equation. Yes, Kausar, I'm all ears. So Carl said, can you go over question 3? 1 second, Kausar. I just saw Carl's 3 part B. What is your conclusion about the effect of large amplitude on the period of the pendulum? So basically you should answer here, there's no effect or there is effect, and discuss why. First of all, you have to explain what happened in your data and then try to say why. Large amplitude would tell me I'm outside simple harmonic motion. Probably you can say it's not amplitude dependent, so you have 2 arguments to discuss. I would think, Carl, this is an open question. Like your answer would be different than Kausar's answers, than Rita, than Romy, than Roy. You know, just discuss your data and try to connect it with the theory. I don't know if I answered your question, Carl. All right. Yes, Kausar, I'm all ears.
Doctor, you just answered one of my questions. I wanted to ask you, no, greater than 10 degrees, no, it's no more no, a simple harmonic motion. So, why did we even try it?
Yeah.
I know it could change anything, but...
yeah, so T is equal to 2 pi radical L over G.
It's not applicable.
Exactly, yes. It's no more applicable. But don't forget, you will deviate from it a bit, not a lot.
You mean the amplitude? No, I will deviate from it.
The period. So the period will not follow 2 pi radical L over G, but it will follow something very close to it. So the deviation is very small. And sometimes using 2 pi radical L over G is a good estimation. Estimation meaning like we know there's a deviation and it could be included in the source of error if you ignore it. And if you don't, you cannot say it's a source of error. So since it's a small deviation, you can still use it with precautions, saying that the real answer, it's not accurate, but we're close to the real answer. Because actually, to be honest, there's no one theoretical period when you have larger than the 10 degrees, unless you can take your pendulum to be a compound pendulum, and then it will depend on many other parameters. Okay? Or otherwise, you can say, I can estimate using this equation. Yani it's close. How do we take, for example, you know, Newton's laws of motion or estimation, you know, because they're not applicable in any universe. We use Einstein's equations otherwise, right? But Newton's laws are still applicable if we estimate in a universe where the speed is much lower than the speed of light, for instance. So this could be used as an estimation, you see? So yes, you have a deviation from the equation known, but it's called a tiny deviation, depending on how big you're far away from simple harmonic motion. I don't know if I'm making any sense.
No, I did understand.
All right. More questions. I love those, by the way. Like you are the best section asking questions. Kudos.
And one more question for the derivatives. Would you give us a derivative that is very difficult to actually solve ولا كلهم بيكونوا مرقوا معنا بالريبورت؟
All right. Again, this is physics lab. It's not a math course, which means I cannot assess you on your math skills. Definitely, we have 4 chapters, so make sure you know the derivatives that we used in those 4 chapters only. Okay? So you're not supposed to be having something out of the blue, no. Okay, so for projectile motion, we have 1 or 2 equations. Incline, you barely have AG sine theta or F equals MA, you know, so you just have to ideas in each chapter, and that's it. And most of them are simple, like multiplication or division. For the pendulum, you have the first square root, numerator, denominator. For the incline, you have the first sine theta, and that's it. And everything else is regular. Okay, so if you train yourself for sine theta, for radical, that's it, I suppose, if I'm not wrong. Yes. Any other questions? Our next item on the agenda, I'm not writing our weekly plans anymore, but I have them in my head. I want to show you the syllabus a bit. Where's the syllabus? I had it open, but when I finished my class, I closed everything, my first section for today. Okay, I wanted to show you where we are and where we're heading. I mean the schedule. The Monday did 1, 2, 3, then 5, then jumped to 7. In your case, we did 1, 2, 3, then 5. And no, I don't want to jump to 7. We don't have to follow Monday. How about we finish 4 first? The reason why we did not do 4, because I wanted to go to campus and record it well. And I did yesterday. So how about we follow the order? And whenever they have a day off, we can do lab 7. So we don't need to follow them. Since they did lab 4 yesterday, it's okay if we do lab 4 as well, and to be focused, you know? And also, it's always smart to follow a reasonable order because it will go along with the course. And why jump if we don't have to? Okay. So only this morning I decided to do lab 4 and not 7. I was about to start lab 7, and here is lab 4. Get ready and let's start. Are you guys ready? I suppose you are. Yes. Momentum and collision. And I know for a fact that you know this a bit from high school and a lot from the course because you started with that. We're not going to do collision of two systems bouncing on each other, head-on collision. We're going to take collision of a system with a wall. So I'm going to study the momentum before, the momentum after, discuss the impulse, the force on the system, and the time of the collision. So a car accident into the wall or something like that. So not two systems bouncing off, which is reducing the problem into an easier, like less parameters, okay? Just to make it experimentally easier on you. The outline I will follow is what's linear momentum, then discuss the impulse momentum theorem, then the experiment directly, discuss it, describe it, and show you the videos that I did yesterday. I'm so proud. Then I'm going to discuss 4 and 5. These are conceptual ideas to discuss, and they are included in the lab report. And I thought, why not discuss it together as a team before you tackle the lab report? Very important. It covers your conceptual understanding of the impulse momentum theorem and wrap it up through abrupt and cushioned collisions. Okay, like wrap up the whole thing. Conclusion. Now, before we start, you tell me, what is linear momentum? If you remember, linear momentum, what is it? Anyone? All right, it's m times v. It's very similar to kinetic energy, which is half mv squared. Why do I need linear momentum if I have kinetic energy? What's interesting about it? Why not kinetic energy بس? Because the other one is also related to mass and velocity. What's interesting about linear momentum? It's always conserved. In other words, every time I have collision, I give you linear momentum, you give me linear momentum. So the systems basically exchange linear momentum before, after. Yes, kinetic energy is not always exchanged in a linear way, you know? So that's what's interesting about linear momentum. And I was interested to see that Kausar is saying that linear momentum is a vector, unlike kinetic energy that is a scalar, which means you don't only give linear momentum in magnitude, you also give in direction. Like the direction could vary before and after the collision as well. And this is very interesting. So linear momentum is actually equal to m times v. By the way, bold represents a vector in many books. Probably I can ask you if you can remember the unit given for momentum. Can you guess, remember anything related to unit? Kilogram meter per second. Yes, obviously. Yes. All right. I wanted to ask something. Yeah. Why do you think momentum is represented by P? And I don't have an answer for this question. Momentum, P. Why is it P? Anyone read anything about this? I just wondered. I think in the old science, it used to be called progress, probably. Probably. I'm not sure about the statement though. All right. I will look into it. And yes, we cannot use M because probably it's going to be confused with mass. But probably in English, like old, it was used to be called progress, probably. All right, now I'm going to start with discussing the impulse momentum theorem. And for that, I need to ask you to give me Newton's second law. What is Newton's second law? What's that? Can you say it again, Maria? Really?
Doctor, in Latin, momentum is impetus.
Really?
That's why they chose P.
No way. Thank you so much. I've never heard of this. Thank you, Maria. Very interesting. Probably I can share this with my students. All right. So, yes. So now back to Newton's second law. It's net force equals ma. Yes, also this is an extra reason card. So F is equal to ma, and I know that the net force, the A is the derivative of the velocity. This is a vector, obviously, this is a vector, and I'm talking about the net external forces. So by simply replacing the acceleration with derivative of v with respect to time, or the rate of which the velocity is changing, I can write this equation as such. Now, m is a constant because before, after, upon collision, the mass is not going to change in most of the cases. You can plug the m inside. So you will end up with d mv over dt, which can be written as dp over dt. So this is the impulse momentum theorem. That is nothing but Newton's second law written differently. Okay? In most of the problems you study in the course, in most of them, the acceleration is constant. Not in simple harmonic motion, but in most of the kinematics problems you tackle. Acceleration constant, meaning that the change in velocity is linear and in momentum as well, which means you can simply replace dv over dt by delta v over dt, but not in all the cases, okay? And this can be written like that, and I like the shape of this equation because I can translate it into words. Delta p is the change in momentum, F is the force applied, and the force applied is needed to change that momentum. How do you change the momentum of an object? You have to give a force over a certain time, all right? In some of the cases, yes, the force is not constant, and this is dp and this is small dt. Keep that in mind. This is only to simplify your problem. If I do understand the linear case of my problem, I can extrapolate in the case where the change is not linear. And we're doing that in the lab. In the lab, the example we're taking is not linear, okay? So the impulse momentum theorem is this. Now, how do I find delta p? Delta P can be found by doing P final minus P initial, or you can do MV final minus MV initial, right? Or you can do F times delta T if F and delta T are known, or you can be given the F versus time, and you can find the area under the curve as well. And this is it's a great method if the force is not constant, because the area under the curve can be actually the integral of f dt if you don't have delta t and you have dt instead. All right, so the area under the curve, in case f is a constant, you will have a graph as such. So this is the case where f is a constant, so the area would be the area of a rectangle, or you can simply do f times delta t. Otherwise, if f is a variable and it peaks out like this upon collision, which is in most of the cases, very applicable, you simply find the area under the curve using mathematical tools, or I don't know, some softwares who would find the areas for you. And we're gonna do this, okay? Now I'm ready to discuss the experiment in general, because as you can see, those are not pictures from our lab. And in the next slide, I'm going to show you the pictures from the lab. In this case, you can see a track, and you can see a certain angle done with extra books. I don't really need an angle. I can simply push the cart with my hand. But the angle is nice because if I have a constant angle, I can have a constant acceleration, g sine theta. Also, by starting the cart from the same initial position, I would know for a fact the speed before it collides with the obstacle. And it could be a constant throughout all my trials. So why use my hand if I can have a constant that I can calculate and I can keep it constant throughout my trials while I vary one variable at a time. So the angle or a constant height is very nice to keep. But I can, this is an obstacle, right? I can insert between the obstacle and the cart a force sensor to measure the force. So I would have motion sensor to describe the motion and a force sensor to describe the behavior of the force. Before discussing the force sensor, which is new to us because we never ever used a force sensor before, I need to ask some of you to tell me a bit about the motion sensor. We used the motion sensor, I believe, once. Yes, only once. Yes. Do you remember how it works? What does it do? If it needs any calibration, if it's user friendly, anything you remember about it. Kausar, what are you? You know everything. So it gives the XT, VT, and AT graphs. That's so true. Every time you need XT, VT, and AT, please use the motion sensor. It's linked to a software, no need to calibrate. It gives us graphs, anything about how it functions. Ultrasounds are used. Romy, do you remember how it sends ultrasounds? What does it measure in return? And why ultrasounds? What's interesting about them? All right.
The speed of the ultrasounds is known. It measures the time, and that's how it calculates the distance.
Thank you so much. So, knowing the speed of the ultrasound, assuming the temperature is regular, like it's known and inserted in the software, knowing the speed and measuring the time taken for the ultrasound to go and come back, it would tell the position, the distance, and therefore the position of the obstacle. Now it's giving ultrasounds continuously, so the position is measured every second. You can plot x versus t. The slope is v, so you can, the software does v versus time, and the software will do a versus time as well by a simple algorithm codes inside. Yes, it will measure the time and calculate the distance, Jana. Of course, it's good to know a bit how your sensors work because it will make it easier for you to handle the motion sensor. Now the force sensor is very sensitive. It is not user friendly. No, I don't like it as an instructor because it gives me a lot of hard time. It has to be calibrated every single morning and it has to be zeroed prior to every single trial. And no, I don't like it. But all four sensors are like this. And let me explain why. First of all, yes, every single morning, like every day, a single morning, if we have like 3 sections per day, we do it once, and that's okay. Unless you switch off the computer for a reason, we don't want to calibrate and save it in the file because by simply changing the force sensor, the calibration is different. Like every force sensor has a different calibration. And I've been doing that since 2006, so you can understand my pain. Anyway, I'm joking. We love force sensors. Not annoying. It's okay. وبينتزعوا كمان, like motion sensors, we have them since forever, and force sensors sometimes they stop working for some reason. Let me explain. Force sensors do not measure force. Yes, I know it sounds weird. They measure voltage. They have a capacitor inside. That's why they need calibration. So every single morning before coffee time, we go to the lab. I'm joking, and I need to give the force sensor a known force, like an actual weight, and measure the voltage measured. And then type inside the software, this volts is equivalent to this amount of Newton. And then since it's linear, voltage versus Newton, the software is gonna calculate the force every time, but the force sensor is measuring voltage every time, okay? So we do it for every single computer because on every single bench we have a different force sensor. It's not like identically calibrated. Now that you know it measures voltage, there's a capacitor inside, and you know the capacitor charges itself. You have to discharge the capacitor. That's why every time you use a force sensor, you have to click zero, like zero your force sensor for it to empty itself for a new trial. So prior to every, let's say you have 5 trials for the experiment, you zero the force sensor, you do trial 1, you zero again, you do trial 2. Sometimes you would forget to zero and it will give you a measurement on top of the old measurement. So it's like students have to do that and we need to remind them. And I will show you how. Now this is a real picture of my hand doing the experiment. This is the motion sensor. This is a certain device to create a height. And this is the protractor. By the way, I don't need to know the angle. I just want to make sure the angle is constant. The angle is not a variable. This is the cart sliding down the incline. This is the force sensor with the bumper. You see the bumper? The bumper because I want to measure the push force and not the pull force. Otherwise, I need to unscrew the bumper and put inside instead a hook to measure the pull force with a wire, for example. So the force sensor would measure the pull or the push. And the FT, the F delta T, who would measure F delta T for me? Guess, motion sensor or force sensor? Definitely, obviously, the force sensor. So the F delta T, how can I find it? I'm gonna look into the FT graph, find the area under the curve. So by finding the area under the curve, I would be finding the F delta T, and this would be done by the force sensor. Now, who will give me MV final minus MV initial? The motion sensor or the force sensor? Definitely the motion sensor. The motion sensor will give me the VT graph. From the VT graph, I will have to find the velocity before collision, just before collision, and just after collision to call it final, meaning after collision. Let's say after collision, and this is before collision. The mass is known because of a prior measurement of the mass of my system, which is this guy. And I can simply find MV final minus MV initial. So, and then I need to compare this guy. Okay, let me change the color. This guy to this guy, like two measurements. Comparing two measurements is tricky because you guys, you know how to compare a measurement, like an experimental value to a theoretical value by doing percentage difference. You always take the theory to be, yes, Kausar, to be your reference, you know, but here you have two experimental values to compare. So everybody would be confused. Which one is the reference? Should I compare A to B or B to A? To be honest, if both are very close, it shouldn't matter if you divide by A or divide by B. So pick one reference of your choice and compare A to B or B to A. It's your choice and it should not be a big deal. Yes, the percentage difference is going to be a bit different if you choose a different reference, but it's okay because it's going to still give you an idea about how close the values are. I cannot say accurate anymore because accurate means how close it is from the theory. Now I'm just comparing how close they are to each other. It's like comparing two sensors, you know? So just to say how close they are, to evaluate my setup probably. I think I'm done discussing. What's that? Okay, let's wait a bit, or let's do that and then show you. No, I'm gonna show you now the experiment. Yes, I think this is the first video. Let me see what's happening here. All right, so I asked the lab supervisor to take the videos, and you can see the videos are a bit different because I asked her to use her phone, and it's not being done on a tripod, so you will see the phone going close and far. You may not like it, or probably you would like it because she can zoom in where I'm actually explaining. No, the area under the curve will be given directly by the software. You're gonna love it, Kausar. You do nothing. The lab report is so easy, by the way. Yes. All right, so here in the first part of the lab, I'm explaining a bit. I took a lot of time explaining the setup because you need to understand the setup to be able to list the sources of errors. Yes, Shana, this is awesome. This is on old software though. So this is the track. I'm explaining the fact that it has a low friction. I'm showing you the motion sensor, reminding you a bit how to use it. The lab supervisor is zooming in, and that's awesome. This is discussing friction. She's zooming in on the angle indicator. I'm explaining in this case that the purpose is to have a constant angle. We don't need to measure the angle. Just make sure to keep it constant. Why constant? If it's not constant, it's okay. But having a constant is easier to analyze my values. I will tell you the variable in a bit. All right. So if it's not constant, it's not a source of error. It's only making it more difficult for me to be able to analyze the variables, the values. I'm showing you how to pick a height. And then I'm explaining that I don't want my incline to be too high, neither too low, something reasonable. I don't want too fast, neither too slow, because it's gonna make my experiment more difficult. I'm also showing you my card and the value, explaining that we measured the mass using a digital measuring tool. And I'm showing you how the motion is gonna happen. Now the force sensor, explaining a bit. I'm sorry, I'm moving too fast probably to your eyes. You can watch the video later though slowly. I'm explaining how I can remove the bumper, how it measures a push and pull, how calibration is done, and how to push on the tear button, okay, to zero my force sensor every single time, okay. And I also explain a bit that the card and the motion, the force sensor should be aligned. Otherwise, the card is not gonna push well on the bumper. And the bumper is the trigger for the measurement, right? So I want to make sure, and probably it's nice to see. The track may slide a bit. So you see the sliding, and this will change the angle. All right, so the track would slide every time this would hit. And this will change the angle of the incline. So if I hold the track a bit, or put the end of the track on an obstacle, that may make sure that the track will not slide, like the whole track will, like the whole system will slide, just to keep it constant. But again, if you have a variable, it's not a source of error because it's not gonna affect the difference between the impulse and the the p final minus p initial, okay. Yes, and this is an obstacle just to make sure everything. And this is how I hold the track a bit. Just hold it a bit. ما بدي إياها تزحط. That's all. The table is very smooth, that's why. So this is describing the setup. The next video, I'm doing one trial or two trials. Let me show you. So here I started from a constant position, constant angle. I made sure that the mouse is under the desk because I don't want to put my hand, neither my arm in front of the card, neither the motion sensor. I will release the card as soon as I click record. However, it shouldn't be simultaneous because if it's not simultaneous, it's okay. I need to measure the collision, which means I will start before it collides and stop after the collision. However, if I don't do that, it's gonna do 1 and 2 and 3 collisions. Many collisions is difficult for me because I will have the area for many collisions. Since I want the area under the curve for only one collision, make sure to stop after the first collision. Very easy. And now you're gonna see our lab supervisor zooming in to the graph and me explaining a bit how the velocity, so this is a VT graph, the velocity is gonna increase because the card is going down the incline, so speeding up. Then you have a sudden collision. Collision means a change in velocity from positive to negative. It's not so sudden because you have a time that is less than 1 second because you know, oh, this is 1 second. This is a quarter of a second. You can see it as sudden, but it's not too sudden. And you have the smart tool, so you can take the x component of the peak and the y component of the peak. The x component of the peak is the time, the y component is the velocity. So you can find the velocity just before collision and just after collision. So this is the velocity. I'm moving the explaining. And here you have slow down as it's going up the incline, and then it's gonna stop whenever it reaches the time axis. I'm moving now the smart tool to take the coordinates I need. and you do V final minus V initial. V final is negative minus V initial, so the end result or the impulse is going to be negative. It's okay. It just means the direction, which is to the left. This is the FT graph. You see it's under the axis because the area is negative. In my case, the impulse is to the left and left is negative, so it's okay. You see the area is hatched in gray. And you will also see the zero. I'm very proud of the zero because with my finger, I actually zeroed the force sensor. If I don't zero the force sensor, well, this will not be on zero. It's gonna add to the area under the graph. It's gonna be something like a constant value. So you see zero before collision, then suddenly you have a peak, negative peak, and then zero again. I zoomed in a bit to be able to see the gray area or yellow area or any hatched area. And you see the software will give you the area directly. It's an FT graph, so the area is Newton dot second. And to be honest, isn't it delta P, F delta T? So yes, it is Newton dot second, and it's also kilogram dot meter per second because kilogram meter per second is equivalent to Newton dot second, isn't it? If you think about it, yes. And this is how I do the measurements. And here I'm gonna add extra masses.
Extra mass to my system. I will keep everything else.
All right, so this is your variable. So you're gonna do the thing with M, initial mass of the core. Trial 2, you add mass. Trial 3, you add mass. Trial 4, you add mass. Trial 5, you add mass. This is your variable. If you can keep that to be your only variable, it's awesome. Analysis is easy. Otherwise, it will be difficult for you to handle many variables, but it's okay because the motion sensor and the force sensor are gonna do the measurements anyway, and you can still compare them. I will not continue the video, you can continue on your own, but what I'm gonna actually do, repeat the experiment, take measurements again, and show you how things are, just to repeat the measurements for you. Now back to the presentation. All right, the angle, okay, increasing the angle will increase the acceleration and it will increase the velocity before collision because it's gonna accelerate faster, like speed up faster before it hits the obstacle. But it's okay. If I keep it constant, the angle, the acceleration is constant, the V before collision is constant, so it will be easier for me to analyze what happens to delta P. It's not wrong to have a variable angle, but I just want less variables. I want VA to be my unknown or my mystery or my something to predict. If I have a variable VA and the variable VB, I will not understand what is delta P. You see? So I don't need to vary the angle. The angle will not affect my work. It will simply have my VB higher. And it will be confusing for me to analyze my values, you see? So that's all. Just let's try to keep it constant. This is what we want. We're not gonna vary the angle. We're gonna try to keep it constant. Okay? Yes, so now I'm repeating a bit. This is the VT graph. So you can see V increasing as the cord is sliding down the incline. Then suddenly you have collision. Again, not too sudden. Yes, it's not only better, Kausar, it's easier to analyze. And all scientists do actually do this. They vary one parameter at a time. Otherwise, your analysis will not make sense. So this is V before collision. This is V after collision. Make sure you take the Y component only because the X component is the time. And you see, this is the delta T or the time through the collision, during the collision. It's very tiny, less than 1 second usually. And then as the cart is going up the incline, it's gonna slow down to a stop. And this is where the stop is. Now for the force, you see the force is 0 and during the collision, it's gonna go up and then down. And this is the area under the curve. This is an example, you know. And if you read the time, you can see that the time is less than 1 second. The human mind would think this is sudden. It's not so sudden though. This can only be seen because it was zoomed in. Otherwise, you will simply see 0 force, then nothing. You will not see the area under the curve unless you zoom in. Okay, these are the real pictures from the video. You see the VT graph, screenshot from the video, and this is the FT graph. and this is the area under the curve, but I'm gonna give you definitely good values. This is the table of measurements that is from the lab report. This is the mass. I'm gonna vary the mass and you will have 5 different measurements. The impulse is the area under the curve. It's gonna be given to you. Just make sure we write the units. VP4 is the one just before the measurement and this before the collision, and this is just after the collision. This will be taken from the VT graph. So this is VT graph. To find the P, you simply have to multiply by the mass, and P after multiply by the mass, and delta P, you do P final minus P initial. And now your job is, which color shall I pick? Your job is to compare this to that. This is measured by the force sensor, and this is measured by the motion sensor. Okay? Yes, so simply comparing probably 2 sensors. By doing the percentage difference is just to compare this to that. Okay? So I'm gonna give you half of the table and you're gonna do the calculations and discuss your values. And that's it for the experiment. And now we're ready to discuss a bit the egg drop contest. I was surprised to find that 2 students of my previous section already did this contest. It's in competition that is done in many schools and in many schools around the world. LAU did it once or twice on campus. I don't know if you guys ever did the egg drop contest. And I was also surprised that the student who did this contest in school actually cheated. And she had no idea she cheated. Or probably she did, but simply she did not hide it from me. I don't know. Have you ever took part of this competition? You've seen it in movies, Jana. Yes. You can find a lot of YouTube videos, like real videos about competitions of egg drop. Can you tell me, Jana, a bit about it? What is it about? Do you remember? Or anything you know about it?
We should basically stand on a surface that is a bit high up and try to throw an egg and not break it while it hits the floor. So we need to find a way to protect it from breaking, even though it's falling from a very high surface.
Yes, I remember at LAU, the engineering department did it many semesters ago. It was sponsored by Red Bull probably, and they had a very high platform, like 15 meters high. And you know, I can imagine the music on campus. We could barely focus in class because of the music, and it was an all-day event. And yeah, I remember one of my students had the egg inside an eggplant. Yes, Romy, can you tell me a bit about your experience?
We just did it for fun. In our class, we wrapped an egg with a hoodie that we had يعني بالcostume تبع المدرسة, and we threw it from the window. And بوقت البreak, we went to the playground to check إذا it broke, but it didn't.
Okay, so I was wondering who was ready to wash the hoodie or to throw the hoodie. All right, I used to do this for my high school students every single year, and trust me, we had a lot of raw egg everywhere in the garbage in the playground. It was really disgusting and so much fun because those students were so creative in the wrong direction, because creativity sometimes when you do this jello and whatever and foam, like shaving foam, and everything eventually will be thrown out of the garbage, doing nothing to your egg. It was funny. Yes, so Romy and her friends casually bringing raw eggs to school, yes, and eventually fighting after school. Anyway, so how do we want to protect the egg? To protect the egg, we need to use the impulse momentum theorem. And to make our egg to be safe, we need to make sure that the force on the egg is very small. So create a design to have a small force on the egg. And to be able to decrease the force, we have 2 options: either decrease delta P or increase delta T, or do both. Okay? But for you to be able to do that, you need to understand what is delta P to be able to control it, and what is delta T to be able to control it. Delta P actually is the change in momentum. The final momentum has to be 0 because upon collision, the egg is gonna stop. The initial momentum, for you to be able to control it and to lower it, you want to make sure that the egg reaches the floor slowly to slow it down before collision. How do you slow it down? Probably create a parachute system like this plastic bag to make sure your egg will fall down slowly. So to have a small delta P, you need a slow motion before collision. Now delta T, be careful, is not the time taken to hit the floor. It's the time of the collision, which is a fraction of a second while you are hitting the floor. To increase the time of the impact, you need to use like a cushioning device. For example, those straws are gonna bend, I suppose, because they're empty from the inside, and probably give the egg some time to stop, like not stop suddenly. How sudden is sudden anyway? I think this is a foaming device. I don't know. A lot of students will use a lot of balloons and wrap the egg around balloons. And trust me, this is the safest because the time of the impact is gonna be huge, like an airbag device, and so on. You can simply wrap the egg with bubble wrap. I actually had a student to put the egg inside the chicken and to throw the chicken. It was funny and disgusting. Yes, I know. I had a student who decided not to be creative at all and wrap the egg in newspaper and throw it. But it works, depending on the grading system, actually. Depends on how high the percentage is on creativity or complexity of your system. So, anyway, if you do understand how delta P behaves and how delta T behaves, it's easy for you to have a small f because small f is actually related to safety. And now, talking about safety, probably somebody can explain to me how airbags actually function and how you can explain it through the impulse momentum theorem. Anyone can try, and please try and do mistakes. It's okay. Yes. How do you believe an airbag actually functions to keep you safe? Anyone? Probably you're talking and I'm disconnected. Yes, Christopher, it increases time of the impact. It deflates quickly. Can you explain, Christopher, how it changes the time and how does it increase it and how does this create a better safety? Christopher, unmute yourself, please. Yes? Yes, say it again.
I think that the force will be lower if we increase the time it takes the driver to hit the guidon.
All right, so the force is lower, and this is the safety we're looking for by simply increasing the time of the impact because of the cushioning mechanism. Like the body of the driver is gonna stop, it will take time to stop and not suddenly to stop. Yes, when collision happens, it deflates and cushions the person, definitely. So the airbag will not affect delta P. So delta P is gonna be MV final minus MV initial. V final is 0, I cannot control it. V initial is how fast I'm actually driving before the actual accident. So the airbag has nothing to do with that. It will only increase the time. Thank you so much. And the time is the time between the car accident and your face hitting the car, So it's not the time before the accident. Be careful about that. All right, now if I need to discuss a bit how the behavior of the force through time would be, we know for a fact that the force is gonna be high. This is the actual force, and this is the time, the duration of the impact. If I increase the time, yes, you see that the force is gonna be low. If I have a small time interval, the force is gonna be high. However, delta P is equal to F delta T, and we know that delta P is gonna be same in both cases, and the cases I'm talking about are abrupt and cushioned, right? So It's the same exact experiment I'm doing, the same car accident. The only difference is abrupt versus cushioned. So same initial speed, same final speed, and therefore delta P is the same. Delta P is the same, meaning the area under the curve is the same. So by increasing delta T, F is small, and by decreasing delta T, F is big. However, the area under the curve is gonna be the same. Now I'm gonna ask you something, but please give me a second because I need to see something. All right, so the question is, I need somebody to tell me abrupt is big T or small t, cushioned is big T or small t. Anyone? So abrupt is small t, yes, because it's happening through a very small time interval. And cushioned is obviously the opposite, so it is bigger t. So which one is safer? Obviously, which one is safer? Bigger t. So cushioned or abrupt? Definitely cushioned, yes. And if I try to draw both graphs again, the one that is cushioned will take more time and a smaller force, and it will give you a graph that is wider and lower. And the one that is abrupt is gonna give you a short, like a narrow time and a very high force, okay? So it's gonna give you a force that is very sharp. Which graph actually is safer, the narrow one or the wide one? I know I'm repeating the question. I just want to make sure that you got it. So the wide curve is safer because it has a smaller force, and the sharp one, the sharp graph, would give you a bigger force, and it's not safe at all. It's very dangerous. All right, I think you got the idea. If I jump to the lab report, we're doing lab 4, so I'm gonna, just a second, I think I should update this app. I'm not sure I can though, because I don't have the license anyway. All right, so you will be asked some questions prior to the values, and this is a general conceptual question. This is the table you need to fill in, and these are general questions to answer. Like you don't have any plot to do, any linear regression to do, any error on the slope, any average, any RMS, any nothing. Very short lab report, please enjoy it. Try, I guess you understood the whole thing because I discussed all the questions through the presentation. You just have to grasp them and to write them using your own words, okay? And that's it for today. You are dismissed and you can stay behind if you have any question. I will stop recording, but I'm staying here